recording here. Right, so yesterday, in yesterday's class, we started the discussion of feedback amplifiers, and the whole concept of putting feedback around an amplifier had to do with the ability to change some of its characteristics. Right, I have a slide here, but I'll correct that a little bit. I used the wrong word. Instead of increase input impedance, here it really should have been improve input impedance, because it improves it in some cases. It has to decrease it in some cases. It has to increase it, and we'll meet that later on today. Right, so I will correct this here. Improve is better, is probably a better word instead of increase on lower or decrease in those two applications here, right? Improve. And well, we saw that amplifiers, there were basically four types of amplifiers here: the voltage, the current, the transconductance, which took voltage in and gave current out, and the transresistance, also known as the transimpedance amplifier. As I mentioned, you may see that. The transconductance takes a voltage and gives you a current. The transresistance takes a current and gives you a voltage out. One application of the transconductance amplifier that I didn't mention, it has to do with something called calibration, right? You use multimeters and you meet multimeters on scopes and various measuring instruments in the lab, and when you go out in the field, you're going to see any number of measuring instruments depending on what work you're actually doing. All of them have to be calibrated. Calibrating or calibration means essentially comparing the readings against a known standard. Right, so when you take a multimeter and you measure a voltage across a transistor, let's say, and you find you have 5.55 volts, right? Because the multimeter is displaying 5.55 or maybe 5.556 volts. How sure are you that that is what is really there? We kind of assume, and it's something that a lot of humans assume, that because there is a number with a decimal point appearing on a screen in front of you, that it has to be true and it has to be accurate. But it isn't necessarily so, and the only way that you know if it is so is to calibrate it, which means that you put something that is known, like in the case of the multimeters, known voltages and known currents, into the device, and you compare it with what against a known value. The values are, of course, standard voltages and currents. One of the things that they use in companies that calibrate these multimeters, like those makers of multimeters like Fluke and some of them, they have a huge transconductance amplifier. It's a big, heavy device when you look at it because of the circuitry involved. But what it basically does is that the exact transconductance amplifier operation, you put a standard voltage in, and it gives you a current, a very, very accurate current that is a multiple of that voltage in, according to the gain of the amplifier. So the ones that I am familiar with, it would take 20 volts in, and it would give you up to 1,000 amps coming out. So it's a very big job, and the cabling and everything is very heavy. But those are the kind of things, like when you want to calibrate meters that read very high currents, like clamp meters and so on, although that's slightly different. You need to pump accurate high current from some source through the meter. And this is where the transconductance amplifiers in that area comes in. And if you ever Google it, transconductance amplifier or calibrators, probably you should check that, electronic or electrical calibrators, you will see them talk about that. These are all things you're going to meet at some point, right? Now, I don't know when, but in your life, depending on where you work, you will come across these devices, and hopefully you'll remember sometime when your hair was still black, or you still had hair on top of your head, or whatever it is, that hey, we spoke about that at one point. Anyway, just a lot of side talk there. So those were the 4 classifications of the amplifiers, and we ran through the models. If you're dealing with voltage amplifiers, you use a Thevenin equivalent circuit for it, and if you're using currents, whether it's at the input or the output, you use a Norton equivalent. And then, right, when we put the feedback on it, right, and this was just a last additional point I wanted to make here. The feedback, we saw that there were 4 types. There were, depending on what you're sampling and what you're feeding back, and that's where the name comes in. So the first part of the name, when you see a name like voltage series feedback, the first term is what you're actually sampling, right? So this is the output. This is what part of what do you call it? What electrical parameter on the output I'm actually going to be sampling. Remember, a bit of it has to be fed back, right? So at the output, if you're sampling, well, you see a name like voltage series, it means that voltage is what is being sensed or sampled at the output. The second term now has to do with what you're sending back. Voltages go back in series, currents go back in shunt, right? So when you see voltage series now, it means that I'm sampling voltage and feeding back voltage. You go later on, current series means I'm sampling current, series means I'm feeding back voltage, and so you go on. So just by the name of it, you could get a good idea of what the actual, at least the amplifier that you're talking about is. So voltage shunt, I'm sampling voltage, but I'm feeding back current. Okay, and then so what sort of voltage, what sort of amplifier has a voltage on the output and a current on the input, right? The relationship therefore is a V over I, so that's resistance, right? If I ask you, therefore, like if you were doing a quiz question and I ask you, okay, what type of amplifier is a current series feedback amplifier? So current series, so current means I'm sampling current, series means I'm feeding back voltage. So current on the output, voltage on the input, therefore that's a transconductance amplifier. Right, so it's an easy way of when you're reviewing this stuff, look at the name and visualize it with a particular circuit. Yeah, sort of a mix and match here. And we went through all of this yesterday, so there's some stuff here to feed, to look on. So let's go on with that. Of course, if you have any questions, feel free to stop me at any point. So before we continue with some of the more, as I told you, this particular topic is a little more theoretical in that it's less about circuit design and more about how you want to make a circuit behave, right? But let's look at some circuit examples just to see what we're talking about. So here's voltage series feedback, right? So based on what I just told you, voltage series means I'm sampling voltage at the output and I'm feeding voltage back at the input. So look at this design. This is a two-stage amplifier here. Some of the things that you may have met before, apart from the feedback resistor. But notice what's happening. I'm taking the feedback resistor is connected back to the emitter of the TR1, the first stage. So there's a voltage being sensed output, and this network of RF and RE. RF and RE form a simple voltage divider, so that the voltage now, the feedback voltage is now developed across RE. The negative feedback is because, of course, TR1 inverts, so that the voltage output here and the voltage behavior on this transistor are out of phase. So when I do this, I'm actually feeding back a minus VF into the TR1, right? So this is a simple way just by one resistor, as we said. You just have to tie it back, and we said that the feedback networks are usually just a passive component or two here. So everybody's seeing that voltage being sensed and the feedback voltage being developed across the emitter resistor here. Voltage series feedback. Yeah? And then, all right, look at this one. This is voltage shunt feedback, meaning we're sensing voltage, but we're feeding back current. And how is that done? Well, we hook the feedback resistor from the collector of the this TR1, this simple arrangement here, back to the base of TR1. How is that going to work again? Because of the voltage developed across TR1, of course, is inverts, right? The behavior of the NPN transistor in normal operation is an inverting process. But the voltage difference between VO and this point here causes a current, a feedback current to flow away from the base of TR1. So in other words, the signal current is coming in here, and part of the signal current is now being siphoned off in IF, and the rest going to the actual input of the transistor. That is a negative feedback behavior, that input, something is being subtracted from the input, and the rest is going towards the transistor. So again, that's a negative feedback part here. This is voltage shunt feedback. Right. Current series feedback, of course, okay. So current means we're sampling current. Series means we're feeding back voltage. And this one is even simpler, simple transistor in operation. We have omitted the bias circuitry, of course, but this could be a simple H-bias small signal amplifier where the emitter resistor isn't bypassed. So at this point in time, the current is flowing through the emitter resistor, and the same emitter resistor is now developing the feedback voltage. Right, so the resistor here is working both as a sensing device for the current and the feedback device for the voltage. Yeah, and you would have met that without knowing it when you did these designs where you have the transistor and you have the emitter resistor, and part of the emitter resistor was bypassed, right? That is when that part is giving you the gain stabilization, but this part here is actually giving you a little bit of current series feedback that does some improvement, as we'll see when we do a little bit more of the lecture later on. Yeah. And then the last one, of course, is current shunt feedback. Mean we're sampling current and we're feeding back voltage, right? Same sort of arrangement. So you sample the current, you're sampling the current here by connecting a feedback resistor back to the base of TR1. Remember, there's an inversion that takes place at TR1, so there's a polarity difference between TR2 and TR1. This point, sorry, yeah. Current shunt, yeah, my mistake. Thank you. We're sampling current and we're sending back current, yeah. My mistake. Yes, so we're sampling the current. How we are doing that is through the feedback resistor here. The current, again, is whatever is going into the base of TR1. Part of it is being siphoned off through the feedback resistor, and the rest is going to I1. So it's the same sort of negative feedback effect that we seeing here. This is in a two-stage amplifier. All right. So all four of them are examples of the types of feedback that we saw before in terms of the sort of equivalent circuit. But this is how you actually do it in practice. There's a lot more discussion, of course, on the calculations. We could get into that, but not at this point. It's not part of the sort of syllabus for us now, because what we could have done is to calculate, how, if I were to design something like this, how would I see like the currents and so on. Unfortunately, we don't have the time to approach that here, which is something I would like to do So maybe in the next iteration of the course, I'd shift things around a little bit. All right, but you have, the important thing is that from what you did before in your first year electronics and some of what you did here, you know how to design amplifiers, you know how to bias the amplifiers, you know how to get from the specs, so you could choose the various components in there. And now with the discussion on feedback and what we're going to do a little bit later on, you will be in a position now to see, okay, if I want to make like a constant feedback amplifier, how to size RF and so on. And you could read the handout that I gave you, has the information on how to go about and figure out a design if you want to. All right, it's not on the syllabus, so don't go reading it up now and then forgetting the important stuff. Okay, right? Not that that is not important, but at least for the purposes of your accomplishing what you need to accomplish with the course, right? So you can look over that and listen to it at, when you're reviewing, and at least get it straight in your head, what it is we're talking about. So we said yesterday, and this is the more correct sort of version of this slide, that feedback can improve the input impedance, but specifically, it will increase the input impedance for voltage, those amplifiers that take voltage in. You remember, it's always an advantage to have a high input impedance when you have voltage coming in, because the higher the input impedance is, the more of the signal voltage is going to be dropped across the input of the amplifier. On the other hand, if you have an amplifier that is taking a current as its input, you want an input impedance that is as low as possible, so it takes all of the current. The current doesn't drop across the source resistance, and you lose, because it's in parallel with that, so you lose a set of current through the source resistance, and less comes to the amplifier. So we're going to see, we'll work through some of the little manipulations, get to sort of prove those statements. It does the same thing with output impedance. The output impedance, of course, are the reverse of the input impedance behavior. Then, of course, it stabilizes the amplifier gain against variation in some of the characteristics of the parameters. We saw that the drawback of that is that it lowers the closed loop gain of the amplifier compared to the open loop gain. And you kind of know that already if you just think about the op-amp specs, that a 741 of op-amp has maybe an open loop gain of maybe 10K. But once you start to put the feedback resistors in it, you start to drop the gain down to, you know, maybe a couple hundreds or maybe in the tens and the like. And then, of course, we improve the frequency response of the amplifier. So we'll touch on those. Let's see how far we get as we go through this, and whatever we don't complete today, we'll finish next time. All right. So let's talk about input resistance. And you'll see sometimes the wording input impedance and input resistance kind of being swapped there. Technically, the more correct term is input impedance, because the amplifier or electronic devices have input resistances, but they also have input capacitances as well. So the behavior really is a little bit frequency dependent, but for our purposes, we'll just treat it as having a resistance alone. And negative feedback influences that, and of course, the nature of that depends on how we apply the feedback. If the feedback is series applied, which is voltage, then remember it's negative feedback. So what happens is that the feedback voltage opposes the input signal voltage. So it basically subtracting from it. And therefore, if you subtract the overall voltage at the input, you're decreasing the amount of input current going into the device. Remember, the input current is really the input voltage divided by whatever is the input resistance of the device. So you reduce the input current, so therefore the overall effect is an increase in input resistance for the amplifier, right? If less current is able to go to the amplifier, that the effect of that less current in is more resistance being met, if you like it. Yeah, fair enough. So again, stop me at any time to comment. Right? If the feedback is shunt applied, meaning current, then the feedback current tends to increase the signal current. Remember, the feedback current is in parallel with the current that is going into the device, so that the signal current now has to be more. If the signal, if the source is seeing more signal current being demanded of it, then as far as it is concerned, the device input resistance has dropped. Okay, and in both of these cases, it is independent of the method of sampling. So it is we're dealing with the input side of things here, so it doesn't matter whether we're sampling voltage or current. What is important at this point in time is whether we're feeding back current, in which case the input resistance falls, or if we're feeding back voltage, in which case the input resistance rises. Yeah, kind of a seesaw effect there. Making sense? Hopefully. Right. So let's look at the, and here I have the word input impedance, but input resistance and negative feedback. So we're back to our, the model. Voltage series means it's a Thevenin model. So we have a voltage source on the input and a voltage on the output, and we're feeding back the voltage. So this is being, if it's voltage series, remember we're sampling voltage on the output, and we're sending back. The important part here now is the series part. So we're sending back a voltage, and the voltage is, because it's a negative feedback, the voltage is opposite polarity, right? Remember the device, forget the feedback, the device, forget the extraneous stuff. The input impedance with feedback is whatever is the source voltage divided by whatever input current. Remember the source, all the source is seeing is this, right? So you connect a source, all the source knows is what voltage it is supplying and what current it is supplying. So as far as the source is concerned, all of this thing with feedback, it is seeing an input resistance with feedback of Vs over In. Yeah? So we could juggle around the numbers a little bit. We know that from yesterday that the feedback voltage Vf, right, with some factor beta VO, remember that's the feedback network coming here, and V in, which is this little bit here now, this is after the feedback, V in is I in by R in, whatever is the input impedance. This is what we're looking at now. Yeah? We also know that at the output side, that VO is AV, you remember it's a Thevenin equivalent, so the output voltage now is a voltage gain by V in, right? And our output voltage is being measured across that point. So we have a little divider with RO and RL. So AVVI appears across this. So the actual voltage here is a little voltage divider arrangement with RL over RO plus RL. Yeah? Simple circuit manipulation there. We also know that the open loop gain, and they watch the little v and the big V there a little bit, right? The little v is the one associated with the Thevenin equivalent here. The big V is the open loop gain, which is totally V out over V in, right? As far as the amplifier is concerned, V out over V in. Let me just put that in a little different color here. So V out, V in, this gives me a capital V, right? This other one here is associated. This is the gain of the device when it's operating, that's the closed loop gain, depending on and that depends on what you actually put it into the amplifier. Yeah. So if we substitute, make some substitutions around, right? We get that we have VO is this. So we're going to substitute for VO inside of here, and then make another little substitution. So we get a capital V in there as well. You do that, then you're getting that V out is a capital V and I in R in. And we plug it back now. As I said, we're plugging it back into this equation, whoops, into this equation here. All right? Just a little bit of manipulation here and straightforward algebra, and this is what we'll end up with now. Right? The important thing is to get rid of what we want is we want to get rid of all the VOs and VINs and VSs and so on. That's the whole object of this. So if you do that, and you remember this little definition that we had on the first slide, that the VS, IS, and whatever is the input resistance that the source is seeing. Eventually, you get it down into this little relationship here. We've gotten rid of all the voltages, and we have now that the input resistance with feedback is the original input resistance, which is this. But we have this factor inside of here, 1 plus beta AV. Now, beta AV is bigger than 1. Right? The AV is whatever is the, remember the A capital V is the open loop gain of this device. So if it's an op amp, it's something fairly substantial. And beta is our feedback factor. Beta AV is bigger than 1. So therefore, this arrangement is now making the input resistance has now been increased by a factor of at least beta AV. Right? If beta AV is much bigger than 1, then this thing inside of here is more or less beta AV. So we're seeing now that the input resistance by doing this voltage series feedback, and the important part here is the series part, by doing it that way, that the input impedance of this device is beta AV more than what it was. Now remember, if you remember yesterday when there was a table where we had the 4 types of amplifiers and the input impedances and the output impedances. The ideal one for voltage series feedback is that the input impedance is supposed to be infinite. Of course, we know it's not going to be infinite, but by being able to, when we put feedback in it, we are increasing it, so we're making the input impedance get even bigger. The ideal is infinity, but the bigger the better. Yeah? Make some sense? The actual algebra and the equations is something you have the handouts on the slides, so you could kind of just follow it through. What I'm going through here is just the manipulations without you know, describing what you're able to read. Yeah. So for voltage series feedback, the what do you call it? The input resistance increases. Right, and as we said, the feedback has increased the input impedance, input resistance by a factor of beta AV. So let's see now voltage shunt feedback. Right, so voltage means we're sampling voltage, but we're sending back current. Right, and remember, if we go back to our slides, what is supposed to happen here is that where are we? Right. If the feedback is current or shunt applied, what we're supposed to see is that the input resistance goes down. So that's the opposite of what we just had. Voltage, the series feedback went up. We just showed that. Let's see what happens with the shunt feedback now. So the shunt feedback, if we're feeding back current, the input part of the circuit here is Norton, right? we're sampling voltage on the output, so the output is a Thevenin output, but of a Norton type input. And if we do the analysis again, remember, as far as this source is concerned, right, this current source is sending what do you call it, a current IS into the device, and the input resistance therefore will be the VI over whatever is at IS. So you keep that as the same kind of thing like before. So the current source doesn't care, it's seeing an input resistance, which is RIF. In this case now, we're manipulating the current equation instead of the voltage. The source is now being split between, the source current has to divide between the feedback current and the input current. This is the useful bit here, right? And of course, because it's voltage shunt feedback, the relationship between the feedback voltage, the feedback current and the output voltage this time is beta. So we substitute IF as beta VO, and we have IN. Follow the circuit through the same sort of thing that we had before, right? In this case now, voltage shunt, right? So this is what type of amplifier is this? Trans what? Output is voltage, input is current. So therefore, the transfer factor of it is V over I. So that will be our trans resistance. Right? So this is our trans resistance amplifier. The output of the amplifier is voltage, the input is current. So therefore, the sort of transfer function will be a V over I, which is a resistance. Yeah? So this is a trans resistance amplifier taking current in, giving me voltage out. And notice what we were saying. If the feedback is current, when you look at it, the input impedance is now reduced by the factor beta Rm. Rm, of course, is the V over I for this device. Yeah? So proving what we said, that if you're feeding back series, which means voltage, the input impedance goes up. If you're feeding back current, the input impedance goes down. Yeah? When you review it, of course, you have the thing, you have the slides and you have the recording, but just conceptually, what I'm saying makes sense? You can see it. And again, just remember, if you're trying to figure it out, if you're feeding back voltage, voltage is going to subtract from the source, or from the signal voltage or the source voltage. So if you lower the voltage, it means that the current going into the device is going to be less. In other words, as far as the source is concerned, the resistance to current has increased. When you're feeding back current, the current now, the source is going to, instead of only supplying I in, it has to supply I feedback because the feedback is being subtracted from it. So if it has to supply that, the source is seeing an increase in current, and an increase in current, as far as it is concerned, means that resistance has gone down. Right? So conceptually, that is how it's supposed to work, and algebraically is what these slides are showing. And of course, what you could do, look at the current series now. So the current series, which is the transconductance amplifier, right? The transconductance amplifier is current in and voltage in and current out. All right. So if it's current series, it means that we're sampling the current output and we're feeding back a voltage. And then, so you could do the manipulations on that. Because we're feeding voltage back, we see that the gain goes, the input impedance goes up. You could follow the And follow it through as well too, just in case I made some typos. There were some typos in the original documents that I was using for this. So um, look at the look at it and make sure, because sometimes when you're writing over equations, and you will know that sometimes you copy something and you forget to change a subscript or a superscript. All right. So you're feeding back series, which means you're feeding back voltage, so you want a higher input impedance. And then the last one, of course, is the current shunt feedback. So that's a current amplifier, current in, current out. So if you're feeding back current, which is the shunt part here, the input resistance is supposed to drop. And if you do the calculation, you see that it's going to drop again by this beta factor here. The amplifier has a current gain, so it's going to drop by a factor of beta times the current gain of that. Yeah? Right, so you could check those, they'll ask too. But the important thing is to always the English here. Right, you see these two slides here, this bit here. If the feedback is series, meaning that you're applying voltage, what happens? And then if the feedback is current, meaning or shunt, meaning current, what happens? And notice we had nothing to do with how we took the output, right? Whether it was voltage or current we sampled, it didn't matter. It's what we're feeding back. Yeah? All right. Your for your purposes and so on, what I expect you to be able to answer sort of questions on is that if I give you a configuration, for instance, if I were to put this in a diagram form and give you something looking like this, right, and tell you, okay, that's the equivalent for a feedback amplifier. What kind of feedback amplifier is that? Or maybe one of the diagrams from yesterday's slide, for argument's sake. What kind of feedback amplifier is that? And two, what would you expect now to be the behavior of the input resistance on that? Would it increase or would it decrease? That kind of thing. All right? Or other type of questions might be to actually give it a circuit and tell you to show me that this little bit happens. All right? In most cases, I wouldn't ask you to draw this circuit from memory. I would give you something and ask you either to identify what it is or tell you what it is and tell you how to prove a particular relationship for that circuit configuration. All right? So you have to know the circuit configurations, yes, but you don't have to know it to the extent we're expecting you to redraw the circuit. Okay? I'll give you those kind of things if that was to happen. Right, so that's input resistance, and let's see what happens with output resistance. So as you would expect, the output resistance also varies. And in this case now, we have to look specifically at how we take the output, whether we're sampling voltage or current. And in this case, if we sample the output voltage, then the output resistance is reduced. And if we sample the output current, then the feedback the feedback increases the output resistance. And conceptually, again, you remember why. If you have an amplifier and you're supplying voltage, you want as low an output resistance as possible, so that of the amplifier, so that most of the voltage would appear across the load. Yeah? If you're supplying current, and this is the load, then you want the input impedance of the amplifier to be high, so that most of the current goes out instead of staying inside of the amplifier. Yeah? Conceptually, that's what the operation of and the importance of the output impedance is. It's a question of how much of the voltage or how much of the current is appearing across the load. In both cases, you want to maximize what the load is getting. That is the whole purpose of the amplifier, is not to keep this stuff inside, right? It's kind of like happiness. You want to keep it inside. You want to spread it out. So you need a low output impedance for happiness. Okay. So how you do it, and this, I have two diagrams up here to show you. We move from one to the other. So what you do here, of course, is a little bit like the Thevenin analysis that you would have done for circuits before. We're going to short out some things and remove a couple of things here. The first thing is the output resistance of the amplifier is independent of the load. So get rid of the load. So the first thing we do is to move the load here. All right, so we're going to take the load out. The second thing now is that if we're measuring output resistance, we want to see what is the resistance of the amplifier looking back into the output terminal. So we don't want anything coming at us from the input. So we get rid of the source. We set the source to 0. Then what we do is to see now what will happen if I put a voltage on the output of the amplifier. We put a voltage now and see how much current flows. So depending on the voltage that I put and the current that I'm supposed to get, I'm now in a position to calculate what is the output impedance of the device. Yeah? So this is kind of like if you actually have when you're doing electrical wiring, for instance. I don't know if you all had a chance to do that, but you do when you actually set up the wiring, there are things like ground testing that you do, right? You're checking to make sure, of course, the line, the neutral are not connected to each other, that the ground is continuous all the way through. And then sometimes what they do in a practical circuit as well is that they do an impedance measurement to see just how high the impedance is on the line on the line coming in. Of course, to do that, you have to disable all the power supplies. You're not going to put a voltage or a mega or an ohmmeter on a device that is live, right? You're going to kill yourself. So the same approach here. There's a little circuit, not your house wiring, but the same approach is here. If I want to see what is the resistance of the circuit from the output coming in, then I have to disable all my sources, of course, set them to 0, and then move the load, because the load is in parallel with everything else. If I try to measure the things, then I'm going to get something in parallel with the load. I don't want the load in. Make sense? Yeah? Right? Okay, and then if you just follow it now, right? So we've set the load, so we disable the current, and the circuit now becomes very easy. The feedback voltage, remember, is voltage series. So we know that the input voltage now is beta times the feedback voltage, right? We have no source to deal with. The current appearing at the output, we put a voltage on the output. The feedback amplifier also has a voltage source inside, which is the AV in, all right? And we, of course, our voltage is what do you call it? Opposite to that, is bucking that. So the actual current in is the difference between those two divided by whatever is the output resistance, this character here. And we make the substitutions for V in here, and then we calculate what is V over I. And here's the arrangement, that V over I is the output resistance reduced by the factor beta AV again. So in this case, voltage series feedback, voltage is of course what we sampling, so that's the output. So the output is voltage. We want the output impedance to fall because we're dealing with voltage. So here we have that the output impedance has fallen by that same feedback factor, beta AV. Yeah? So we're proving it again. All you have to do, of course, to remember to prove it is you have to remove your source resistance and remove the load. Sorry, move the source voltage and remove the load resistance. So very straightforward. And then if you were to put the load back now, remember the load appears in parallel with RO. If I put the load back here, right, then as far as the output is concerned, it's going to see RO in parallel with that. But you already know that this has fallen, so that the parallel combination is going to fall even more. It's going to be less than ROF anyway. Fair enough? Make sense? And then, of course, you could do that, take that same approach. Well, this was just repeating what I had. Take that same approach for the other topologies as well. So once you're dealing with voltage out, notice the output impedance falls. If you're dealing with current out, notice the output impedance goes up, which is what you want. Right? The output impedance, remember this is inside of the device. So if this is higher, it means more current is going to be sent outside, because this is the output impedance is in parallel with the load. So if this goes up, it means more for supplying current, it means more current is going to go out onto the load. Yeah? All right, so I will stop the discussion here today, because the other two things that we have to talk. It's actually fairly small, but it's interesting discussions, and we'll finish it off next time. How the feedback improves gain and how the feedback improves bandwidth. All right, two small things, and we will finish off that in our next class on Monday, please God. Yeah. So to give you a shorter class today, because everybody fighting for projects and so on, and we're in a good place at this point. We just have that little bit finished. So for all intents and purposes, we are at the end of what we had, apart from two small topics here. Right. So in the meantime, well, I'll try to get through the midterm marking and put up some questions and so on. Maybe I'll take some. Well, I'll put some past paper questions and so on from the last time. I think you may have had. If they're not on this site, I'll try to put them up. What was done in the last iterations of the course is the discussions are similar, but the stress that I made here is different. So I'll try to put questions that are similar to what I will be asking you in your exam coming up. So if you pull up a past paper question, or you go in the library and you manage to retrieve some older exam papers and so on, don't be too concerned if you see some questions that are looking strange and that we haven't covered it. It's because we haven't covered it, and you're not going to be examining on it. All right. We're flying a little bit blind from your perspective, in that you don't know what to expect, but whatever I'm asking you is going to be things that we do here, not whatever you see on the past paper questions, right? If I give you some past paper questions to do, it's because those are the kind of things that I could ask you on, or that you should be able to answer. Yeah? Fair enough? So any questions before we end today?